All right, this is lecture number 8. So we're going to be continuing to work on the gas law problems worksheet. So what we're going to jump into today is right here, gas destiny. The destiny of gases. What is their future? I'm sorry, I'm being told that's density. Oh, that's gas density. So you already know something about gas density. You know they're not very dense at all. Very few particles per unit volume. But what we're going to do right now is the 13.5 section, and we're going to, there's 3 gas density problems. All right, so let's take a look at how we can take our combined gas law and do a derivation. We're going to do some algebraic manipulation, those 2 big words, and throw derivation into that. It'll sound intimidating, but basically all we're going to do is change some things around and make this combined gas law formula into something that's kind of doable for the density of a gas. So we know that density equals mass over volume. Okay? D equals M over V. And the first manipulation that we're going to do is we're going to say, well, if that's true, then V, just put the V over there and drop the D down there, V equals M over D. So if you take the mass divided by the density, then you get the volume. Well, volume is in this equation, correct? We have a V1 and a V2. So what we can do is rewrite this and make sure this is in your notes. I might ask you on the test to show how you can take the combined gas law and the equation for density and manipulate them into a simplified form. All right? If we take a look at this, all you did is for V1 there you put M1 over D1, that's mass 1 over the density 1, and then over here mass 2 over the density 2. Now of course the density can change, right? Because you can scrunch it down and make it more dense. You can expand the container and make it less dense and spread out. But if you look at this equation, mass is going to be a constant because the gas sample can be measured out as a constant. So as a result of that, you can leave the mass out of this equation, and then you have P1 times the quantity 1 over D1, P2 times the quantity 1 over D2. So the masses are no longer a part of this equation. So basically, to figure out these densities, we need pressure and temperature, since the mass is going to be constant. All right, and we figured volume in by putting in this form of the density equation. So that is not considered a very clean way of writing a formula. If you have 1 over D1, you can multiply both the top and the bottom by D1. So if you multiply this by D1, those are going to cancel out. So then the D1 is essentially on the bottom of the equation here now. Okay, so same thing here, D2, those will cancel out, multiply the bottom by the same thing, D2. So inside the box here is the derived formula for figuring out gas density. Now, it's very important that you know that you don't have to go through all those steps every time you do one of these problems. Again, you would only have to do that if I said, how can the combined gas law formula and the density formula be simplified? And this is the answer to that question. So what we can do is we have now another gas law. And you know a bunch of them right now, right? You got Boyle's and Dalton and Charles and Amonton's and combined gas law. Now we've got a formula for density. Good thing this next test is going to be open note, huh? All right. So we got a lot of these formulas, and you should label this in your notes. This is the formula for gas density, or the one we're going to use. There are other ones. We use kind of a different one in AP chemistry, but this is going to work very well because it's kind of mathematically it's very similar to using the combined gas law, except for you have the density in the bottom. All right, so we look at question number 20. All right, so here is the way it's phrased. It says sulfur dioxide has a density of 2.927 grams per cubic decimeter. Now remember, a decimeter is, I'll just use this little container here, it's about that size right there, okay? And if you picture a cube about that size, that's what a cubic decimeter is. It's 10, remember, of the centimeters is your little finger. So if you picture that, that's the volume. Now, another way of saying that would be liter, right? Because it's the same thing. A cubic decimeter and a liter is the same thing, but use the units that are given to you in the problem. And then they said that's what its density is at STP. So you should be getting really good at knowing what the standard temperature and pressure are in any given conditions. And then it asks, what is its density at a new pressure of 120 kilopascals? So that's going up because standard pressure in kilopascals, 101.3 kDWB. You got it. And the temperature of 50 degrees. So the temperature has also gone up because 0 degrees Celsius is STP. All right, so how do you start a problem like this? Same way as if you're doing Boyle's law, Charles' law, combined gas law. Write the formula. Boom, you got your first point for just recognizing this is a gas density problem, and let's start plugging the numbers in. All right, so the problem said that it had this density at standard temperature, 273 Kelvin, and pressure, 101.3 kPa. So those are your initial conditions. You go over here and they said the pressure is going to go up to 120, and the temperature is also going to increase by 100 degrees Kelvin, which, by the way, is also 100 degrees Celsius. It's a 1 degree increment in Kelvin is also equal to a 1 degree increment in Celsius. They're the same scale, you just add 273 to the Celsius temperature. And again, you can see the importance of converting your temperature. Think about this. If you would have left that as 0, ask how your math teachers feel about taking something and dividing it by 0, or ask your calculator how it feels about that, because 0 times 2.97 would be 0, and all bets would be off, and you'd be done with the problem because it would say undefined. So very, very important to remember to keep, whether it's Charles' law combined like we did last time or the density problem. Convert those temperatures into Kelvin by adding 273. You're going to get really good at that. Okay, so the math on this one is a little bit tricky because this is on the bottom. So solving for D2, I think, in my opinion, the easiest way to do this would be to cross multiply again. Take the ones on those dimensions right there. So I'll just punch this in for you here. 273 times 2.927 times 120. And then I always hit the enter key just to be on the safe side. Well, if I multiplied on this dimension, when I go here, each one of these I'm going to divide by each one on the other dimension. So you just go like this, and you see you've got that answer divided by 101.3. Hit the enter key again. Divided by 323. Hit the enter key, and I get a 2.93. And it would be limited to 3 sig figs because of your temperature. So you can see that for all practical purposes, because you increased both the pressure and the temperature, the density really remained the same on this one. Okay, so the density 2.93 grams per dm cubed. Now, if you want, and you can do this in your notes right now just as a clarification, you can rewrite it as, those dimensions. This is what I typed into my calculator. You can rewrite that like this if you want. So it's this angle right there, cross multiplying, divided by the two numbers on the other dimension. And I think you did a little bit of that when you were solving for a temperature in combined gas law. So the math, a little tricky, but it is just sort of a basic algebra level. Okay, so let's go ahead and do 21, and try this one on your own. Hit the pause, try it on your own, and see how you can do before we turn you loose to finish the other ones, or the other one. Okay, so hit the pause. Welcome back. Let's see how you did. So we got gas density. All right. They had said that with this one, the initial conditions were at STP. All right. So at STP, boom and boom, and then they went down like this. Now, in terms of this temperature, that's going to be 3 sig figs. So you could put a bar over that 0. You could put a dot there, or in the setup of the problem, just make sure you do something to indicate that this is a significant figure. So 300 exactly is what that is. You can see when I rewrote it here, I put a bar over it just to indicate this. And this is optional to do that, to rewrite with this. But hopefully when you solved, you got 2.96. And again, you can always check the answers in the book. Okay, so I want you to do 22 on your own to make sure that you're feeling comfortable with that. So and then we can move on to the next video, because today we're doing 2 different laws, and this is the gas density. So do 22 on your own, make sure you're getting the right answer and you're feeling comfortable with this. Okay, so again, the bar on the top there, I just forgot to add it until this final slide, so make sure that you do that. Okay, all right, see you on the next lecture.